What is sound? What is happening when we hear music like this? What's happening plays his violin. He draws his bow across a string and sound is produced. What is making the noise? Using a stroboscopic light, we can see that the string is moving back and forth along its length. It's oscillating. By dragging the bow across the string, Dominic is causing the string to move. But how does the sound get from the string to our ears? There's nothing to see, but perhaps this will help. It's a soap film, and the sounds produced by the violin cause the soap film to move. In between the two, something must be moving. It's invisible, but this is a representation of it. Dots are air particles. The vibrating string causes the particles of air immediately surrounding the instrument to move. What do you think produces the sound in this instrument, the didgeridoo? Steve is blowing down the tube. It looks rigid enough. What's vibrating here? In fact, Steve is blowing a raspberry down the tube. His lips are vibrating and making sounds which pass into the didgeridoo. They set air particles in the instrument moving. Sound waves move up and down. So the violin and the didgeridoo have something in common. They both produce vibrations in the air. What else can we find out about these vibrations? We can't see sound, but we can get a representation of the sounds on an oscilloscope. Let's listen to the violin on its own. We'll fade out the others and we'll freeze the picture. What can you see? There's a pattern there of peaks and troughs. Listen to the didgeridoo. He only seems to be playing one note, but it's still a complicated display. Similar to the violin, but a different pattern, though it still shows peaks and troughs. So do all sounds look like this? Well, here's a much simpler sound, a tuning fork. In close-up, we can see that the tuning fork is vibrating, so the air around is being disturbed by the prongs. And yes, on the oscilloscope, the shape has peaks and troughs like the other two instruments, but it's a much smoother, more regular shape than the violin or the didgeridoo. It looks like a wave. Why? Let's look at this again. The air is obviously being disturbed by the moving prongs, and if you look closely you can see a pattern. The air particles are oscillating about a point, and energy is being transferred from one particle to the next. It looks like a wave, and it's called a longitudinal wave because the air particles are oscillating along the length of the wave in the direction it is travelling. If we were to translate this into a transverse wave, as on the oscilloscope, this is how it would look. The peaks represent compressions of the air, the troughs represent rarefactions, but it's important to understand it's only the shape of the wave that moves forward. Individual particles merely oscillate about a point. Back to the music. But let's separate out the violin again. Here's his sound. Freeze it. Can you make more sense of the pattern now? There's a wave in there. It's got a bit of a jagged edge, but it's a regular pattern. The distance between two peaks or two troughs is the wavelength. Here's Dominic playing a single note. The shape of the wave is complicated, but the length is constant. Watch what happens next. The sound gets higher, and on the oscilloscope, the length of the wave gets shorter. By counting the number of complete waves passing through a given point in 1 second, it's more easily understood in our particles diagram, we get the frequency of the sound. By the way, sounds travel much faster than we're showing here. As far as measurement's concerned, 1 cycle per second, and that's a very low frequency, is known as 1 Hertz. If the wavelength is shorter, what happens to frequency? Frequency increases as the wavelength decreases. A higher frequency means a higher pitch in musical terms. Dominic can put his fingers on the strings to increase the pitch. In effect, he's shortening the strings. But what about the didgeridoo? Can Steve get a different note out of that? No, he can't. He has to use a didgeridoo of a different length to alter the pitch of the sound. Of course, there's another way of raising his pitch. Speed him up like this. But that's cheating. What else can the oscilloscope tell us about sound? We're going to cheat again. Turn down the volume and look what's happening to the waves. Their height is reduced. The height of the peak from the horizontal centre line is the amplitude. The bigger the amplitude, the more sound energy the waves carry, the louder the sound. So they are all connected. Wavelength, frequency, amplitude, and those of describing properties of a sound wave. But watch and listen to this. It's an electric bell sounding off in a bell jar. Let's take the air out with a vacuum pump. What's going to happen? The sound of the bell has disappeared. Why? Sound needs a medium to travel through. As we saw earlier, sound is conveyed by passing energy from one molecule to another. Take away the molecules, as in a vacuum, and there is no way of transmitting the energy. That's why we can't hear the bell. And if we put our violin player in the jar, we wouldn't be able to hear him either. Here's another way of looking at sound, through a piece of gadgetry called a spectrum analyzer. This isn't showing waves, it analyzes the frequencies in a sound. Lower frequencies on the left in red, rising to higher frequencies on the right. Let's hear and see some single notes. Freeze the image and what can we see? Not one peak as you might expect, but several. Why is that? The other peaks are frequencies that are also part of the sound, but how come they're there? The violin has a fundamental frequency. It's the frequency of the sound when the whole length of the string vibrates. But the string also vibrates in other ways, in equal halves, thirds, fourths, and so on. These subsidiary vibrations are known as harmonics. The fundamental frequency is usually heard as the basic pitch of the musical sound. Let's look at some other sounds. Here's the didgeridoo. It sounds lower, deeper than the violin, and the display is different. The main peaks are to the left, the lower end of the frequency range, but there are still other frequencies, the harmonics, that are higher. The size of the peaks gives an idea of the relative strength, you could say importance, of the frequencies. Here are the congas. And here's the voice. As on the oscilloscope, they all produce different patterns. Most established musical instruments fall into one or the other of the types we've seen. They can be grouped the way they move air to produce sound. Strings, where a stretched string moves the air. Wind, where the player's blowing moves a column of air. Percussion, where something, typically a skin, is struck to move the air. That's fine, but so far we've only considered musical instruments. What about this? Is this music? Most people would say it isn't, but it could be.
Brief number 2. I like collecting noises and using gadgets to make music, so I was asked to create the same piece of music electronically.
What's so attractive about electronic music? Well, for a start, you have complete control over the sound. I was using a microphone to capture on tape some noises from around the college. Microphones may be familiar, but do you know how they work? This is another type of microphone, and here's a stripped-down version of it. The round plate is a sensitive diaphragm which vibrates in time with the sound waves. The movement is converted into an electric current. That feeds into a tape recorder which stores the electrical signal digitally. So what's the difference between music and noise? This is the music, and here's the noise. What do you notice about their waveforms? Let's look on the spectrum analyzer. See the differences? They're both made up of many frequencies, but it's not the number, it's the pattern of the frequencies that affects the quality of the sound. Basically, if the pattern is regular, it sounds like music. If it's irregular, we generally call it noise. And of course, what's noise to some is music to others. Paula's going to use other electronics to make some more sounds. This is a digital synthesizer, and again it brings sounds completely under control.
Okay, try something else. Try that.
Recreate the sound of a violin? No problem.
Okay, try that. Okay, let's try a little bit more like this. Okay.
Add some more.
Like any other digital device, a synthesizer uses numbers to achieve its effect. It's full of gadgetry like oscillators and tone generators, and the great thing is you don't even need to understand how they work. Tweak a few knobs and faders, you can get any sound you want. Drum sounds, they're in another box of tricks. Okay, but what about Simon's voice? Surely that can't be synthesized like violins and didgeridoos. Well, it could be, but it would be very difficult. There's another bit of technology that can do something with it.
Let's try moving this.
In the studio session, Simon's voice was recorded on tape. That tape recording can in turn be played into a sampler. And this is a graphic display of the sound. But here's the clever bit. You can chop it around, repeat it, loop it. The sampler plays all those noises collected around the college as well. All the electronic sources, synthesizer, drum machine, sampler, can be brought together in a computer using a piece of software called a sequencer. It will play all the noises at exactly the right time and in the right order.
Okay, stop.
There's only one problem. There's nothing here like a string or a column of air or a drum skin that is going to vibrate. So how does the sound actually get to our ears?
Yeah, that's fine. Okay.
In fact, all the electronic signals need to be amplified, that is, put through an amplifier and made louder. First, the sounds are fed through this. It's a mixing desk. It allows the different sounds to be put together and the volumes, in effect the amplitudes, to be adjusted so that a balance of sound is achieved. The sound goes from the mixing desk via the amplifier to the loudspeakers. Take a close look at this one. How do you think it works? A loudspeaker, like a microphone, is a transducer, which means it changes one form of energy into another. Electrical energy from the amplifier is changed to kinetic energy in the moving loudspeaker cone. The speaker pushes the air around it, setting up sound waves in the air again, and those energy waves are in turn picked up by our ears to be converted into sound. That's where the sound comes from for the final electronic performance. Here it is.
The unit's available on video, price $14.99. The study guide at $4.95 includes program outlines, background information and a series of student activities. To buy these items by credit card...
Last. Fuel pressure's fine. Valves are all sealed. Nearly ready to go. Good job too. I've about 12 hours left on my life support system. Another investigation.
Steve is blowing down the tube. It looks rigid enough. What's vibrating here? In fact, Steve is blowing a raspberry down the tube. His lips are vibrating and making sounds which pass into the didgeridoo. They set air particles in the instrument moving. Sound waves move up and down. So the violin and the didgeridoo have something in common. They both produce vibrations in the air. What else can we find out about these vibrations? Dominic is causing the string to move. But how does the sound get from the string to our ears? There's nothing to see, but perhaps this will help. It's a soap film, and the sounds produced by the violin cause the soap film to move. In between the two, something must be moving. It's invisible, but this is a representation of it. Dots are air particles. The vibrating string causes the particles of air immediately surrounding the instrument to move. What do you think produces the sound in this instrument, the didgeridoo? What is sound? What is happening when we hear music like this? What's happening plays his violin. He draws his bow across a string, and sound is produced. What is making the noise? Using the stroboscopic light, we can see that the string is moving back and forth along its length. It's oscillating. By dragging the bow across the string, we can't see sound, but we can get a representation of the sounds on an oscilloscope. Let's listen to the violin on its own. We'll fade out the others and we'll freeze the picture. What can you see? There's a pattern there of peaks and troughs. Listen to the didgeridoo. He only seems to be playing one note, but it's still a complicated display.